What is a field? Okay, so we started out by talking about how many objects are needed for there to be a force. Well, since an object can't exert a force on itself, there need to be at least two. But does gravity disappear because there's only one object that I'm looking at? If the Earth were to disappear, would the moon still have a gravitational pull? Well, yes. So how can we describe how strong the gravity is somewhere without having another object to interact with? So that's where gravitational fields come in. So let's start with what is a force field. So a force field will exert a force on an object in its vicinity. Let's look at some examples. Like a magnetic field. If you've played with iron filings next to a bar magnet, you'll notice that the magnet itself attracts the iron filings in a certain pattern, and those follow the field lines. An electric field acts similarly. I turned on the Van de Graaff machine today in class, so hopefully you got a visual of kind of what the electric field lines look like around essentially what would be a point charge. Or a gravitational field. Now this one, unlike magnetic and electric fields, is much harder to visualize. So, what is a gravitational field? So, because it's a gravitational field, it has to do with the force due to gravity, which is caused by things with mass. So every object that has gravity, every object that has mass, has a gravitational field. The Earth, the Moon, the Sun, Jupiter, me, and you. All right, and so it describes the gravitational force exerted per unit mass. We'll get to that more later. Okay, how do we represent it? Well, we can draw a picture or we have an equation. This is a picture of some gravitational field lines. So, because a force is a vector, so is our field. The field lines always point towards the object with the mass because gravity is an attractive force. So, where the field lines are closer together, that's how you can tell the field is strongest. You'll notice that they get closer together as they get closer to the center of the Earth. For each of the red circles, along any given circle, the acceleration due to gravity or the force due to gravity on an object placed there would be the same at any point on that circle. The direction is different, but the magnitude is the same. You can actually, for the purposes of this class, think of those field lines as continuing all the way to the center, because as we treat objects like a point mass at the center of mass, we're not going to worry about figuring out the calculus that goes into between the outer shell and the center. Now, at the center, they do all cancel out. We'll get to that later too. What is it good for? Well, we can calculate acceleration due to gravity at any point in the gravitational field, or we can calculate the gravitational potential energy in a two-body system.